Hey guys, so today we're going to talk about ionic compounds. Now, before we do this, there's a few things that we need to review that we talked about a few weeks ago. So, first off, elements and compounds. Okay, an element is when you have only one kind of atom. So, for example, copper, gold, oxygen. If I had a chunk of copper, it would just be all copper atoms. Or if I just had some oxygen in a container, it would only be oxygen atoms in there, even if they would be bonded together to make O2. So that is an element. A compound, on the other hand, is when you take two different elements and they bond together to make a new substance. For example, water, which is neither hydrogen nor oxygen, it's hydrogen and oxygen bonded together to make an H2O molecule. Okay? Salt, NaCl, completely different than sodium, which is very poisonous and explosive, and chlorine, which is highly dangerous to breathe in. But if you mix them together, they react, they turn into sodium chloride, table salt, completely new material. Okay? And then sugar is actually made out of three different elements. That's a complicated one. C12H22O11, carbon, hydrogen, and oxygen. So these are all compounds. All right? Now, when you have a compound, we have this idea called the law of definite proportions. Water, that's a compound. It's made out of hydrogen and oxygen, but it is always two hydrogens for every one oxygen. Okay? Always 2 to 1. This is the law of definite proportions. All right? Hydrogen and oxygen for water always comes in this ratio, 2 to 1. Law of definite proportions. They always combine in this specific ratio to form this compound. If it's not a 2 to 1 ratio, it's not actually water. In fact, there's actually an H2O2, which is hydrogen peroxide, which is not water at all. It's a different compound. Okay? So that gets us into law of multiple proportions. We have two elements that can actually form one compound with one ratio and then a different compound with a different ratio. Those are still two different compounds, two different materials. All right? So, for example, there are actually two compounds made out of chlorine and copper. All right, so if we mix 27.9 grams of chlorine with 50 grams of copper, and then if we mix 55.8 grams of chlorine with 50 grams of copper, same amount of copper there, okay, but different amounts of chlorine, they will produce two different compounds. One of them, by the way, is exactly double the other, so we can tell that one would be copper chloride with one copper and one chlorine, and then copper chloride with one copper and two chlorines, 1 to 1 versus 1 to 2. Okay, so here's kind of what they would look like here in terms of their ratio. Same elements, two different ratios, two different compounds. Okay, so that's something we talked about way long ago in Chapter 3 that I wanted to refresh your memory on. Something we talked about right before the Thanksgiving break, though, was the idea of a metal versus a nonmetal. Okay, so on the periodic table, we have metals, nonmetals, and then we have these metalloids, these sort of semi-in-between metals. All right, everything on the left of the periodic table, with the exception of hydrogen, is a metal. Everything on the right of the periodic table is a nonmetal, and then the metalloids are the ones that are right there in between on that stair-step line there. It's important to know which one's a metal and which one's a nonmetal because metals are the ones that have a low ionization energy, and so they are likely to lose electrons and become positively charged when they become ions. Nonmetals, on the other hand, they like electrons, they have a high electronegativity, so they will be more likely to steal some electrons, gaining electrons and gaining a negative charge. Okay? So we have two different things happening here, gaining electrons and losing electrons. Formation of salt. This is also something we talked about before the break. So sodium, okay, is a metal. It is here on the periodic table. It has a low ionization energy. It wants to lose electrons. All right? Chlorine, on the other hand, is a halogen. It is a nonmetal. It has a high electronegativity. It is more likely to gain electrons. So sodium has 1 valence electron and chlorine has 7. Sodium is likely to lose its 1 rather than gain 7 more to get 8. Chlorine is just 1 away from 8, so it's just going to try to gain 1. So it gains it from the sodium. Sodium gives it to chlorine. So that electron moves over to the chlorine, and now we are left with a sodium that has no valence electrons, or rather it doesn't have any in the third anymore. Now it's filled out its second, so it's completely full in the second, but nothing in the third. And the chlorine has a full third energy level there. So these two ions, positively charged and negatively charged, are attracted to each other, and they form the compound sodium chloride. Okay? So an ionic compound is when we have a metal and a nonmetal that exchange electrons with each other. This forms a more stable system because it gets each of them a full outer energy level, one by going a full the one below it, and the other one by having its outer one completely filled. When this happens, energy is going to be released. It's an exothermic process. The structure of an ionic compound, when they actually form, because they're positively and negatively charged, they form this crystal lattice, where it's a repeating pattern of the positive, negative, positive, negative, positive, negative. Okay, the reason it's this pattern is because the positive and negative, since they're attracted to each other, it's a repeating pattern. Positive is never going to be near a positive. A negative is never going to be near a negative. Okay, but they are going to be next to each other. So you have positive, negative in this repeating pattern, balancing out those charges. Now these are very strong, rigid structures. This positive and negative attraction and forming the structure here, it's very, very strong. Typically things that are ionic or ionic compounds are going to be hard, very rigid things like rocks. Almost every rock is an ionic compound of some sort. So they're very, very hard, difficult to break, okay, and they're very, very rigid. Make good building materials sometimes. So a couple of terms here that we talked about before the break. Cation. The cation is the metal one. This is the one that loses the electrons, and therefore it's going to have a positive charge. Because if it, say, had 11 protons and 11 electrons before, it loses an electron, so now it's 10 electrons and 11 protons. It's going to be more protons, positive charge. The other one is the anion. That's the nonmetal. This is the one that gains electrons. Since it now has an extra electron, which are negatively charged, it has a negative charge. So, for example, sodium, in that example I had before, that's the cation, okay? Positively charged ion. The anion is chlorine, the negatively charged anion, right? So when we draw the Lewis dot structure of these ions, okay, representing the formula here, sodium, we would just draw it with no electrons, but we put brackets around it and include that positive charge. That's the cation. Chlorine, we would draw it with all 8 valence electrons, just the valence electrons now, not the inner orbits, not the kernel ones, with a negative charge around it. Okay? The charge of the cation is going to be the number of electrons it lost, the number of valence electrons, and the charge of the anion is always going to be the number of valence electrons that it gained. All right? Now, this crystal lattice that I talked about, repeating pattern of positive, negative, we can actually write what's called a formula, okay, or a formula unit. That is essentially what the repeating pattern is. So in this case, since it's equal amount of sodium and chlorine, the repeating pattern is an Na and a Cl, just one of each, and then that just kind of repeats over and over again throughout the entire structure. Now, this is not the only pattern that can exist, one of each. There is possible to have 1 to 1, 1 to 2, where you have twice as many of one of them as the other, 1 to 3, where you have 3 times as many as one to the other. You even have 2 to 3, where you would have 2 for every 3 of the other. Okay, so these are some of the formulas, the repeating patterns that you can have, and that's what we call them. We call them a formula or a formula unit. This is the simplest whole number ratio of positive ions, those cations, to the negative ions, those anions. NaCl, that was 1 to 1. That is all review. Everything I just said should be review. The next slide is going to be new material. Okay? So, talking about these formulas for ionic compounds, what do they mean, kind of representing here? All of these are neutral. Okay? All of these are neutral, meaning that the charges that they have perfectly balance each other out. How do we actually get these ratios, these 1 to 1, 1 to 2, 1 to 3, 2 to 3 ratios I was just talking about? First off, when we write the formula, something called a subscript there. The subscript is that little number down below. That tells you the ratio of ion to ion in this compound. Okay, so for example, the Na2O, the one right there in the middle, that is a 2 to 1 ratio, 2 sodiums for every 1 oxygen, repeating pattern there. The 2 represents the sodiums, and then the oxygen, there is no number, so that one is just 1. We basically don't write any 1s when we write the formulas. All right? Now, how do we figure out these ratios? It's all about the charges on the ions. If they are the same charge, okay, that means the positive charge and the negative charge perfectly cancel each other out when they stick together, and so it'd be a 1-to-1 ratio. However, a lot of times you can have maybe a positive 1 and a negative 2. Right? That is actually the case with the sodium and the oxygen here. Sodium is a positive 1 and the oxygen is a negative 2. So we don't have this 1-to-1 ratio because the charges are not equal. We actually are going to have more of whichever charge is smaller. Okay, so the sodium, in this case, we have positive 1 to the negative 2. We have to have a positive 1 and another positive 1, 2 of them, to equal out the negative 2 of that oxygen. Okay, so you're always going to get more of that smaller charge based on the ratio of what those charges are. All right, so let's practice this just a little bit. Representing a neutral compound. If I have two ions, they're going to come together. One's positive, one's negative. Okay, and based on those charges, it's going to determine the ratio of the positive to the negative, and we'll be able to write a formula. So, for example, sodium has a positive 1 charge and bromine has a negative 1 charge. Okay, so the positive 1 and the negative 1 perfectly equal each other. So that means that in that repeating pattern, it's going to be one of each repeating over and over again. It's a 1-to-1 ratio. So the formula here would be NaBr. Okay, one of each. One sodium, one bromine. Okay, now for calcium and chlorine, however, calcium is a positive 2, chlorine is a negative 1. These are not equal. Because calcium is higher, I actually need 2 of the chlorines, so we have a negative 1 and a negative 1, to perfectly add together and cancel out that positive 2. So this would be a 1-to-2 ratio. Okay, 2 of those chlorines in order to equal that positive 2 of the calcium. So the formula here would be CaCl2, 2 of the chlorines. All right, now be careful. The charge on calcium is positive 2. The charge on chlorine is negative 1. I have 2 of the smaller charge, not the calciums. Okay, it's not about which one has the positive 2. It's about what do I have? How many of them do I have? Okay, so let's try another one. Lithium with a +1 charge and oxygen with a -2 charge. Again, not equal. So which one do I have more of in this case? I'm going to have more of the lithium with a positive 1. So a positive 1 lithium and another positive 1 lithium to cancel out the negative 2 of the oxygen. So this would be a 2-to-1 ratio. Formula would be Li2O. All right? Li2O, 2 of the lithiums. Magnesium has a positive 2. Sulfur has a negative 2. Now in this case, even though it's 2 and 2, you'd think maybe the ratio is 2-to-2, but it's not. Okay? It's not the same thing as the charges. In this case, the charges are in fact equal to each other. So when they're equal, it's 1-to-1. All right? We have equal amounts of both of them. So be careful about this. It's not the same thing. It's not going to be the same number as the charges. Sometimes it is, a lot of times it is, but other times, really what it is just the ratio of one to the other. Okay, so if they're the same, it's 1 and 1. So this would be MgS, right? Aluminum, positive 3. Bromine, negative 1. So in this case, we would have a 1-to-3 ratio. I would have more of the bromine 1. Okay, so aluminum, I'd have 1 of them. Bromine, I'd have 3 of them. So it would be AlBr3, right? Iron with a positive 3 charge and sulfur with a negative 2 charge. Now this one's tricky, all right? This one's tricky because if I were to say double the sulfur, then it would make negative 4. Like a negative 2 and a negative 2 makes negative 4. That doesn't quite equal the iron, okay? But if I triple the sulfur, negative 2, and then another negative 2, that gets me a negative 6, which is a multiple of the iron. So in this case, I could have 2 irons and then 3 sulfurs, and then that would be equal because it'd be 3 plus 3 equaling 2, 2, and 2. So this would be a 2-to-3 ratio. So this is actually kind of tricky there, sorry. So formula for this one would be Fe2S3. Okay, Fe2S3. All right, last one for my examples. We have lead, which has a positive 4 charge, and oxygen, which has a negative 2 charge. Now remember, it's about how many of them do I need to equal the 2 charges. The ratio is not the same thing. It's not going to be the same numbers. We're not going to have 2 and 4 here. We're going to have 1 and 2 because it takes 2 of the oxygens, negative 2 and then another negative 2 to equal that positive 4. So the formula would be PbO2. All right? So this is figuring out the ratios of positive to negative ions, cations to anions, to equal each other, and then writing the formula. That formula represents what that repeating pattern is in the overall structure, that crystal lattice. Okay? Quick note. When you're writing the formulas, always write the cation one first, and then write the anion. Okay? So we always, as a convention, just to keep things in order, we always write the cation, the metal one, and then we write the anion. So there's an order here when we write the formulas. Okay? Your turn. I want you guys to pause the video and try to figure out what the ratio is between each of these pairs of cations and anions, and then write the formula. So go ahead and practice a little bit, pause the video, get an answer. Got an answer? Okay, so this first one, positive 1 and negative 3. So that is a 3-to-1 ratio, so the formula is K3N. Next one is a positive 1, negative 1. So that is the same, so 1-to-1. So the formula is CuI. Next one, positive 2, negative 2. Those are the same. So this one's going to be a 1-to-1 ratio. So the formula would be FeO. Next one, positive 1 and negative 2. So this would be a 2-to-1 ratio. Formula would be Ag2S. Okay? Next one is a positive 4, negative 2. All right? So this one, we would need a 1-to-2 ratio. Be careful of that. Formula would be SnO2. Next one is a positive 2, negative 3. Now this one's tricky. It's at 2 and 3 again. So this one we would have to have 3 and 2. So this would be Sr3P2. Okay. Last one here. Positive 3, negative 1. So in this case, we would need a 1-to-3 ratio. 3 of the bromines, by the way. So 1-to-3, so CrBr3. All right? And that is figuring out the ratio of positive to negative and finding the formula of this compound made between these two ions. All right? An ionic compound. Now, how do we know what charge these ions have? Well, it all has to do with, first off, whether it's a metal or a nonmetal. And you're always going to have a metal and a nonmetal in an ionic compound because it's always a positive one and a negative one. All the metals are positive. All the nonmetals are negative. Okay? But it also has to do with which family it's in. Okay? So the very first column of the periodic table, this is the alkali metals with hydrogen. Even though it's not an alkali metal, it also forms the same charge. Okay? It fits in as the reason why we actually put it here. So everything in this family always forms the same charge when it forms an ion. It always forms positive 1. Okay? The next family, the alkaline earth metals, everything here, they have 2 valence electrons. They're going to lose them, so they're going to form a positive 2. Okay? This family here, the boron family, everything here, at least all the metals anyway, they lose 3 valence electrons, 2 S's and a P, by the way, and so they form a positive 3 ion, typically. Everything in this family here, this is where it gets a little tricky. You may notice that this is about half metals, and it's got some nonmetals now. Now we're starting to get into the ones with nonmetals. Okay? So this family, the carbon family, the ones that are metal, they're going to form positive 4. The ones that are nonmetal, they're going to form negative 4. Okay? So something like carbon will gain 4 electrons, but something like lead will lose 4 electrons. Metal versus nonmetal here. Okay? Now that's actually true for pretty much all these ones that have both metals and nonmetals in them. All right? Now you may notice that there is a pattern as we move along. It goes positive 1, positive 2, positive 3, positive 4. Okay, so the next column, bismuth, that metal down there, most likely would be positive 5. All right, we don't use bismuth very often, but it's pretty much the only metal that kind of exists in that column, so I'm not going to include it when we get into this next one. So this next column here, in the nitrogen family, with the exception of bismuth, most of these are nonmetals or metalloids. So these ones, I'm just going to include the negative one here. These would typically do a -3 charge. Okay, so nitrogen and phosphorus, sometimes even arsenic. Okay, -3. The next family, oxygen family. Okay, most of these ones are also nonmetals, so these would be -2 charge. Okay, they're going to gain 2 extra valence electrons. This last family here, halogens, they are all nonmetal, and so they will all gain a -1 charge. Right, so there's a pattern here as well, starting with the carbon family -4, then nitrogen family -3, oxygen family -2, halogens -1. Now you may have noticed I completely did not do the noble gases. Okay, why didn't I do the noble gases, this last family here? It's because that one doesn't react and doesn't form compounds. So this family here, it's important to note, never has a charge. Okay, they don't form ionic compounds. They don't form any compounds. So it's important to note they don't have a charge ever. The first family with a charge is the halogens, the one next to it. Now I also skipped the transition metals and the intertransition metals. Why did I skip these? Because they're a little bit more complicated, because they can form several different charges. So we're going to talk about those later in a few days. And I'm essentially either going to tell you the charge, or I'm going to not use them for the next couple of days. All right, so we'll have a new video just on the transition metals and the intertransition metals in a couple of days. Okay? Otherwise, the family tells you what charge it has, and there's a pattern. So let's try it. Try figuring out the charges here. So I want you to try this. This time I have another set where you're going to try to figure out the ratio and the formula, but this time I did not tell you the charges on these elements. So you're going to have to figure out what the charge is. For example, the first one, sodium and fluorine. The charge on sodium is typically, for that family, the alkali metals, +1. And fluorine, which is a halogen, charge on that family is typically a -1. Okay, so this would be a 1-to-1 ratio, formula NaF. Okay, so go ahead and pause the video and try the rest on your own. Got an answer? Okay, so calcium, typically a +2, iodine, typically -1. So in this case, we would have a 1-to-2 ratio. The formula would be CaI2. Aluminum, +3, oxygen, -2. So with this one, we have that 2-3 again. So we would have 2 to 3, 2 of the aluminums, 3 of the oxygens, okay, in order to make those equal. So the formula would be Al2O3. That was a tricky one, all right? Magnesium, typically +2, sulfur, -2, okay? So these are the same. So this would be a 1-to-1 ratio. So the formula would be MgS. Potassium, K, is typically a +1, and nitrogen is typically a -3. So this would be a 3-to-1 ratio, giving you K3N. Gallium, it's in the boron family, so it would be typically a +3. And phosphorus is in the nitrogen family, so -3. Right? Those are the same charge. So 1-to-1. So GaP would be the formula here. Lead. It is a metal in the carbon family. So because it's a metal, it would be the +1, not the -1. It'd be +4 for lead. And then bromine would be -1. It's a halogen. So in this case, we have a 4-to-1 ratio, or excuse me, a 1-to-4 ratio. 1 of the leads, 4 of the bromines. So it'd be PbBr4. Okay? Now naming these compounds. How do we name them? Why do we call it sodium chloride, the NaCl1? Why don't we call it sodium chlorine? Sodrine, chlorium. I mean, why do we have these names? Well, there is actually a naming rule here, naming rules. So for a couple of examples here, I've got a couple of examples here. Here are the rules. First off, Name the positive one first, the cation. Use the element's full name, okay, whatever that positive one is. And we write that first one first in the formula, and then we're going to name that first one first, okay? So positive one first, just name the whole element. Then we're going to name the negative one. However, we're going to change the ending. So we're going to drop the ending and add the suffix IDE. So they're all going to end in "ide," right? Not chlorine. We're going to drop the ending and change it to chloride, okay? Now, do not include any information on the formula ratio in the name. Even though sodium chloride is a 1-to-1 ratio, we're not going to include that as part of the name. Okay, it's just naming the pieces. So NaCl is sodium chloride. I named the Na part, sodium, then the chlorine part, the Cl, and I changed the ending to ide, sodium chloride. This next one here, calcium, okay, bromine, which I changed to bromide, so calcium bromide. Now, I'm not including any information about the fact that it's 1-to-2. Aluminum and oxygen, two pieces there. We'll change the ending of the oxygen to oxide, so aluminum oxide. No information about the fact that it's 2-to-3. Just aluminum oxide, just the pieces. Okay? This last one here, cesium, and then sulfur, which I'm going to change to sulfide. Okay? Cesium sulfide is the name of this one. That's how you name a binary ionic compound. Binary refers to the fact that it's two elements. Hinting at something we're going to get into about a week and a half. We are starting to talk about ionic compounds with more than two elements, but for now, let's just stick with two elements, binary ionic compounds. Okay, binary means two, so that's what we're going to stick with for now. So your turn. I want you to try a few. This is the same slide we just saw a few minutes ago, where I had you guys find the charges and figure out the ratios and write the formulas. Okay, so the same slide here, so you can go back up to those examples that you already have written down in your notes. I want you to now name these 7 ones. So pause the video, name them. All right, here we go. So this first one here would be called sodium fluoride. Change the ending of fluorine to fluoride. Next one, calcium iodide. Iodine changes to iodide. Next one, aluminum oxide. I think that was one of my examples in the previous slide that I used before. Next one, magnesium sulfide. Sulfide. Sulfur changes to sulfide. Next one, potassium nitride. Nitrogen changes to nitride. Next one, gallium phosphide. Phosphorus changes to phosphide. And the last one, lead bromide. Bromine changes to bromide. Okay, lead bromide. And that's how you name them.